Swayam Prabha. Digital India. Educated India.
Maybe we start the lecture, so let me welcome to day 5 of our lecture. Today we will be talking firstly about grain boundary diffusion in metals. As I said, we are strictly focusing on metals because the course is on high entropy systems. Diffusion description, diffusion evaluation, diffusion measurements would be very dissimilar, very different when we would change from metals to covalently bonded material like semiconductors or ceramics, because maybe you know from your courses, if you have a defect like a vacancy inside of a metal or inside of a semiconductor, what is the most important difference between these vacancies in terms of the vacancy properties? The mobilities are very different, yes, but why?
Because in matter they are in free conduction zone, like they can move easily, but in semiconductor they need to cross a barrier to move.
But that's for the electrons, right? But we're talking about atomic diffusion. And for the atoms there is no band gap. But it's related to electronic properties because you change the band structure if you take out an atom. And that means, in effect, you are creating a charge to any defect. So if you go to a covalently bonded system, the charge equilibrium locally is violated, which means there is an excess charge associated with each defect of the crystal lattice. That means that there is, in addition to the entropic terms to describe diffusion, there are coulombic terms to also drive diffusion, affect diffusion, which means that all the diffusion equations, all these partial differential equations which we use to describe diffusion must become much more complex because you have to add the coulombic terms into that picture. This is why we are staying with this very simple case of metals. There we have a Fermi lake, right? So the conduction electrons all go into kind of one state, and we don't have any internal charges in the system because of having a metallic system. This is why description of diffusion in general is simpler in metals as compared to non-metallic materials. This is what we are now talking about. We have a polycrystalline microstructure and we have defects. And these defects could be dislocations, they could be, so basically quasi one-dimensional short circuit pathways. They could be the grain boundaries. So I indicated this here as a slab of material. And obviously we have to also think always also in experiment about a free surface as a diffusion path. In addition, we also have diffusion if the temperature is high enough or the time is long enough to go through the volume. What we will now do is we basically in experiment as well as in the description take the idea of a polycrystalline material, but we forget about volume diffusion, we forget about dislocation pipe diffusion, and we forget about free surface diffusion. It is more easy to neglect volume and dislocation pipe diffusion because they are slower. So we could mentally think we just do an experiment for a sufficiently short time, so we will not see an effect of volume diffusion, we will not see dislocation pipe diffusion, but this one will be faster, so we will see grain boundary diffusion. The point is, surface diffusion is even faster. And so mentally as well as experimentally, we have to take out this part, and I'm going to show you how this is done. But conceptually, now we are just focusing on a system that has many grain boundaries and that the free surface is not there. So let's think about an infinite polycrystal. And let's say it is somehow dislocation free. That is the picture we are using. And as indicated before, the grain boundary diffusivity is one of the fastest, basically the second fastest. So this is here what we are talking about. When we think about this grain boundary diffusion process, there is a geometric feature coming into play, right? It's the grain boundary thickness or width. How wide is a grain boundary? In a relaxed polycrystal, and it's a common high angle grain boundary, random, so not a special grain boundary. What would you think? How wide is it? Absolutely, in the nanoscale. In the lower or in the higher, so 10 nanometer or 1 or 0.1? No, it's actually 0.5. For transition metal, transition metals and well relaxed, random, high angle grain boundaries. It's about 0.5 nanometer, 2 lattice constants. So it's basically that the distortion of the crystal lattice extends like 1 interatomic spacing into each of the grains, which make up the boundary. For well, for pure non-transition metals, it's similar, but there not so much data is actually known because the diffusion measurements to measure this grain boundary width have not been done. For alloys, it's more complex because you have always a tendency to have segregation, and so you have an additional strain field by these different atoms going to these places and segregating at the boundary. And they might not only segregate in the mathematical boundary plane, but also to nearby lattice sites. And that makes the definition of what is the width of the boundary a little bit more complex. So you would then need to define a structural width, a chemical width, maybe a width depending on the strain distribution as a function of space across the boundary. These values could vary a little, so it would give you something like, again, between 0.5 and maybe up to 2 nanometers. And that depends very much on the thermodynamics of the system, like how large is the segregation tendency, for example, of a material. So this is why it's then a little bit more complex. We can, for all these alloys, have proper measurements and proper definitions, but not all the definitions give the same mathematical value for the width. So there are some empirical rules which are very helpful if you do not find the information on a specific system. And basically, as I have told you on Wednesday, diffusion is a thermally activated process. So you have the typical Arrhenius type relationship for the kinetic factor. So the grain boundary diffusivity has a prefactor. And an activation barrier, right? And this all tells you, because you relate the activation barrier to the thermal energy kBT, that it's again a thermally activated process. And so, as a rule of thumb, there are these relations for the different lattices, FCC, BCC, HCP given, where, like general parameters for the prefactor, which has to do with jump frequencies and entropic contributions, is given, and also where the height of the activation barrier is related to the melting temperature, absolute units Kelvin, of the specific system. So you see that basically the higher the melting temperature, the higher the lattice stability, the tendency is that you get also higher activation enthalpy for grain boundary diffusion. Warning, these are rules of thumb. So you can get, if you are working like in an environment where you need to design a certain annealing treatment or get a first shot at an unknown system, you can use these parameters to calculate what roughly will be the grain boundary diffusion coefficient at a certain temperature, because you plug in then the real temperature here, and then you can derive the numerical value, and so you can do a first experiment, and that will show you, is this rule of thumb applicable for this system, or is it rather not applicable? But the details will vary a lot from system to system. And there are two value combinations given. This is the more recent one. And most of the people prefer these values by Gust, just because he actually measured grain boundary diffusion coefficients. And he took also values from our lab a lot, while Brown and Ashby did this prior to most of the grain boundary diffusion measurements. So they are mostly based on more theoretical assumptions. And so this is why the values vary a little. So if there is doubt, I would rather prefer using the approach and the numerical values by Gust over the ones by Brown and Ashby. Now, when we think about grain boundary diffusion, we have to first think about grain boundaries. So, how many degrees of freedom does a grain boundary in a normal, pure metal have? 5 macroscopic degrees of freedom, exactly. Are there additional ones, or are these 5 all there is? Who would think that there are more than 5? There are actually 8. 5 are the macroscopic degrees of freedom, but there are also 3 microscopic degrees of freedom. So you gave the right answer concerning 5. Can you explain to your colleagues what these 5 degrees of freedom are? It exactly is. You see these 2 common types of boundaries, which could be made by having 2 absolutely equal grains. Again, we bring them together. And now we can make a grain boundary by tilting or by twisting. This basically gives you the following picture for a grain boundary. So you have done some operations so that there is a misorientation between the two crystal lattices, so the lattice planes are not oriented in the same way. Now mentally, you now shift these two grains on top of each other, because so far I have only talked about how the orientation relationship between these two grains is. I have not given you any clue on how the grain boundary plane is sitting, right? And whether it is symmetric or whether it is asymmetric and has been inclined. So all of these informations on how the misorientation between the two grains is and how the boundary plane is inserted in this configuration of misoriented two grains coming together gives you these 5 degrees of freedom. So 5 degrees of freedom describe the misorientation, plus the position plus inclination of the grain boundary plane. So this is a direction of the grain boundary normal. And since it's a grain boundary normal, we only need 2 parameters to describe it. So we have 3 plus 2 is 5 degrees of freedom. This is something which we can measure experimentally and which we can control by, for example, annealing treatments, by deformation process or so. The 3 microscopic degrees of freedom we cannot control. Nature controls it. And this is then basically the local relaxations of atomic positions in the grain boundary plane to minimize the stresses locally at the interface between the two crystals. So we can use, for example, EBSD, electron backscatter diffraction, in order to measure all of these 5 degrees of freedom. So you have a complete characterization of the 5 macroscopic degrees of freedom by this very beautiful and very powerful method. The 3 microscopic degrees of freedom are only accessible so far by simulations. So this local shuffling, the local relaxations are really atom by atom type of processes, and we cannot have an experimental view on these processes. And also we cannot control it. Nature does it according to the 5 degrees of freedom and the local misfit, local distribution of excess volume, and so on. We will see later on an indication that still these 3 microscopic degrees of freedom are very important. So internal interfaces, grain boundaries, as I said, 8 degrees of freedom. Tilt, twist, translation are the ones which are macroscopically accessible. The microscopic density degrees of freedom are not accessible, but they minimize mass energy. Now, when you think of a grain boundary, maybe you have this picture in mind. Right, so you see here very nicely, this is a TEM, or more correctly, a high resolution TEM of a low angle or small angle grain boundary. 2 crystals come together and you can nicely see you have a misorientation of the lattice planes. And this gives you the misorientation angle theta. You also see these funny symbols. They are the dislocations which have basically been aligned. They have not been aligned, they align themselves because that minimizes the total energy stored in their strain field. This is why if you have many dislocations, you get cell formation, low angle grain boundary formation. And the nice picture replacing atom columns by balls in red is given here. Now, what happens if I now increase the misorientation? We talked about it. Then basically the distance between these dislocations becomes smaller. At some point they are going to overlap. So this is a problem, because this is what we know. When we think about misorientation between two grains, given grains, and plot their excess energy, the grain boundary energy, then we have first this linear relationship, and that's basically based on dislocation energy. Or it's basically an excess energy, right? So, and then the Reed-Shockley equation tells you how to calculate this. But you will see that when you do the calculation according to this model, you get a deviation from linearity, and basically you also would get less and less dislocation energy because of more and more overlap of the cores. So this must not be a good description for high misorientation angles. So for the typical grain boundaries which we see in a polycrystalline material, which we can identify by microscopy, it's mostly the high angle grain boundaries, and they are actually not covered by this dislocation-based description because dislocations would come too close. Additionally, if you have a real material, not a computer simulated one, you always have impurities, right? Because of mixing entropy reasons. There cannot be a pure material. These are geometrically necessary dislocations, exactly, yes.
If my grain boundary separated SSDs are there, presents are there, they want this energy calculation, because cellular structure in gold material, this model, because this difference is due to that, sir?
It is due to the difference that you have, I mean, the geometrically necessary dislocations are defined as the dislocations that are necessary in order to accommodate a certain macroscopic misorientation or strain. And this is true for the small angle grain boundaries. If you now have higher misorientations, then this model doesn't work anymore, because you would need to have more GNDs as you can put along the boundary plane, because the distance between the GNDs would become so small that the cores would overlap. And if cores overlap, then the dislocation is not longer an entity that can be described as a dislocation. So it would basically mathematically not be a high density of dislocations, but some kind of common super dislocation or something like this. But also, if you bring them too close and they are, they are parallel, then they repel each other. So this is again as if you have two atoms that come too close. You cannot be, because the Lennard-Jones potential tells you if you are coming too close, you get this very huge, very steep increase, which is basically a repulsion you cannot overcome. And this is the same for the dislocation. So it means this 10 to 15 degrees cutoff is really a cutoff between dislocation-based description and the description that must be different, because single independent dislocations can no longer describe the grain boundary character.
Like if my grains have twins also.
Yes.
I am calculating my misorientation through EBS.
Yes.
That gives some misorientation, which include this twin boundary also.
Yes.
Can I correlate with energy of dislocation, like if I want to say
No.
Overall?
No, because the twin boundary is a boundary that is very special. It has much lower excess energy, so it's almost zero, because if it's a perfect coherent twin boundary, the name already says, right? It's coherent because all the lattice planes connect to the other lattice planes. There is no excess volume, almost, just a little bit, and it means that the excess energy density of that boundary is almost nil. And there are no dislocations because it's coherent, right? So in terms of the energy calculations, you can basically, this is why in EBSD you should always look for the fraction also of the twin boundaries, because they should be taken as zero in excess energy contribution.
But here, if I know misorientation for twin boundary, I can put in the equation and then I can get energy of.
Well, yeah, you have a large misorientation for the twin boundary, right? And so, yeah. So you just have to assume, I mean, I will come to a plot in a few slides where I will show you this, what I mean. But in principle, you have to assume that twin boundaries are boundaries which do affect a lot how dislocations transmit through a grain and also through that boundary or not, because they are really obstacles. But in terms of stored excess energy in your material, you can count the twin boundaries out because they contribute only very little. Yeah, so segregation is not included. Yeah, this is what I just told. So you have this picture of low angle boundary, and important is that, you know, this correlation between misorientation, angle, and the distance between these, in this case, edge dislocations. And this is why we have a reason for the cutoff at about for dislocation-based description. So it means when we are talking about diffusion in high-angle grain boundaries, we need to just think, free our mind, forget about dislocations at the moment, and just ask the question when we now have these grains coming together at a high angle, any odd angle you can think of. How is the structure of this grain boundary plane look like, and how is it constructed? This is an artist's view, which actually is a very early computer simulation. Today I would call it artist's view. And you see there is a grain boundary transition zone, because you could kind of see that in this region atomic positions are not so much, not all of them, or a high fraction is not corresponding to the original lattice positions. If you now look at this structure, what do you think? Do you feel comfortable in accepting this as a model for a high? No. Why not?
It's literally an artist's view. Today we have major computational models. We can definitely create a simulation and then we can observe and conclude them, not just blindly looking at an artist's view and then start jumping straight to the conclusion.
Very good. If you now would do mentally high power MD simulation or even ab initio simulation, what would you expect to be the difference?
The atomic representation.
Yeah, I mean, the atoms are given as let's say, simplified. We still talk about in many metals of rather spherical objects. So let's say first approximation, even in most sophisticated simulation, this would be the picture. But if we think now of this region, would you think it would appear similar in the best simulation of a boundary there is, or would it be different?
Many dislocations should be there. It's only one
Yes.
So like this location is sink of grain boundary sink of this location. So too many should be there. The gap is like one atom.
This is absolutely correct what you say, but think about very good paper by Gleiter and Pumphrys. They have observed how a dislocation is driven by external stress into a grain boundary by doing snapshot TEM analysis and observing the strain field of a single dislocation. At that time, high resolution was not yet possible. What does a dislocation? You're absolutely right. Dislocation, grain boundaries are sinks for dislocation, so they move into the boundary. What happens to the dislocation once it's in the boundary, in a high angle grain boundary? It dissociates, it loses its character. It can become a secondary grain boundary dislocation, but then the Burgers vector of that secondary grain boundary dislocation is different from the original Burgers vector, which is defined by the crystal lattice it was coming from. So it means dislocations, once they went into the gap, into the sink, are not longer the same dislocation. They split up, they dissociate, they become something different. They also become excess volume. And this is the important point here. Right? So this has too much excess volume. You can almost fit an atom inside of these gaps. So this is really just a coarse-grained, rigid point of view of cutting two crystals. You have atomically rough surfaces, you bring them together and you see, in some cases you have good registry, less excess volume. In some cases you have bad registry, high excess volume. And now these 3 microscopic degrees of freedom come into play because they basically serve for maybe this atom going here, this atom going here, this one going here slightly, this one moving a long way. And so the 3 degrees of freedom, which are microscopic, relax the high angle grain boundary structure and reduce excess volume. Right, so it means that this is maybe only a first stage structure, which is very short-lived and transitional in nature. And then nature would apply its possibilities of atomic shuffling, short-range kind of diffusive jumps into the free volume which is there to fill it in the most efficient way. Only then the grain boundary structure of high-angle grain boundaries has been built, and then it can be again described by different methods. And these different methods are, for example, the structural units models. They have been very successful, even though they are quite old. So they were invented in the 1970s. And what you basically see is this, right? So this is before relaxation, and this is after relaxation. So it means just as a function of time, the structure would go from here to here. This is the initial cut. We just cut 2 crystals, bring them together. Then you see that all these positions are kind of defined with respect to the crystal they are adhering to, but the boundary itself is much too disordered, much too high excess volume values associated with it. Then this shuffling occurs, and so it means that there is now a very more ordered structure in the high angle grain boundary plane, and also much less excess volume. And also the distribution of excess volume along the grain boundary plane is more uniform. It's not completely uniform because you still have concentrations here and maybe less here or here. But overall, it's reduced. You also see why the width of the boundary as having roughly 2 interatomic distances is rather correct, because you can fit this structural unit nicely into this effective thickness. This is the structural units model. But it's more than just shuffling atoms around and waiting for the lowest conditional free enthalpy to be found, because it also predicts that there is a very small number of structural units that are necessary in order to describe any high-angle grain boundary. It's really beautiful because it's only 7 Euclidean bodies in 3D. You see here a 2D representation, which are necessary in order to make up any of the grain boundary structures. What happens if we now take this picture, which is at a certain misorientation of the 2 grains, and we now change the misorientation to higher values? Is this structure able to adopt that change in misorientation? It will be to a certain extent, and then you need a second structural unit which has different geometry. And if the difference, this is an ideal, like a highly symmetric misorientation, so you only need one structural unit in order to accommodate the misorientation and to have still a rather densely packed and highly ordered grain boundary zone. If you now deviate from it for small angles, still this one unit will be able, with some distortions, to accommodate the misorientation difference. If it's becoming too high, a second structural unit will be introduced, so you have then 2 different units along the boundary plane, and they have different periodicity. So the distance between equal units will be different for the 2 types. If you go more and more, the number density of the second type increases and the number density of the first one decreases until you reach another symmetric position, which then is made up of only the second structural unit. And then if you go further, maybe a different one will come into play. And so this is the structural unit model, and the importance is the periodicity along the grain boundary plane. So there are given units, and the energy minimization is controlled by having them equally spaced with a certain periodicity along the grain boundary plane. And this is a very nice model to work with. It also has some slight problems, because what we do observe in nature is that when we have a certain grain boundary described by a certain arrangement of structural units, and we do not change the misorientation of the material, but change the temperature, we can sometimes see that there are transformations of these structural units. There are phase transformations, structural phase transformations in the boundary plane. And people have termed this complexions. So the whole work on this topic can be found under the name of complexions, grain boundary complexions. And complexions has been invented as a term for saying grain boundary structure or grain boundary phase, because the local structure of this grain boundary plane will be different from the adjacent crystals. And if you remember Gibbs' phase rule, this might be a problem of having too many phases in your system. In end effect, it's no problem, because it's a conditional equilibrium. These phases will only exist in the grain boundary plane as long as the grain boundary is there. So we're not talking about complete equilibrium, because in complete equilibrium, grain boundaries are not existing. But these complexions then are not included in the structural units model, because this model relies only on a geometrical description based on misorientation and inclination of the boundary. Special boundaries. Here we come to your twins. This is, again, a nice picture of a twin boundary, and this is showing a coherent twin boundary, right? So there is no, you could say there is almost no defect there, because all the positions of any atom in this configuration is a lattice position of the original lattice. However, orientation changes, so the grains do not continue ad infinitum as in a single crystal, and this is why there is a small energy penalty. This is the grain boundary energy as a function of misorientation. You can also see that this coherent twin really is at the bottom of this curve, so it's having a very low excess energy. But once you change slightly either the misorientation from ideal or the inclination of the boundary from ideal, then the penalty in energy will be very high. So it means that when you do your analysis with EBSD on your microstructure and you find the twin boundaries, you have to make very sure that when you take these boundaries out of your total energy calculation, that you only take the coherent twin boundaries out. If you have many twin boundaries which show deviations from the coherent twin boundary, then you will basically be somewhere here on these curves, right? And so the excess energy then might be quite high. But you can, normally you can then, you have to go to each specific boundary and then you can look really at both the misorientation angle of the two grains as well as the inclination of the boundary. You get the full description, but you can only do this boundary by boundary. You don't get it in like the total summary, so it's more work. But in EBSD data, it is, this is one of the informations you get for each and every boundary.
We put only there that sigma CSL, sigma 3 boundary, then we get that way.
Yeah, so yeah, but then you get basically an information about this, and maybe you are here, right? Could be. So it's more intricate because you see that these minima in energy, they are very steep and very narrow. So it means slight deviations give you a lot of excess energy increase. That's a big problem. And overall, maybe doing an analysis of the whole microstructure like you do in EBSD, and you press a button and you get number fraction of CSL boundaries will not give you a good answer. Yeah. So maybe it's a good way to check some and see, because it would depend also on whether a twin boundary has been generated as a deformation-induced twin or whether it's a grown-in twin. The grown-in twins tend to have lower excess energy, so they are more like the coherent twin. But if you induce them by deformation, because of this being a directed process involving dislocations, many of them and so on, often they are not the coherent twin boundaries, and then you can count them energetically also as high-angle grain boundaries. They will still have a reduction in excess energy as compared to the random high-angle grain boundary, but the reduction will not be so large.
So from the tip of the twin, we can identify it's like deformation twin or like.
This is very difficult. Yeah, you can look at it in terms of shape, yes. If it is very straight over a long distance, and you do not see many dislocations associated with it, like strain fields, I mean, you can look at the kernel misorientation maps associated with the boundaries, and if this is rather a uniform color, that means that there is no strain variation along the boundary, and then it is a good indication that this might be a grown-in twin. For a deformation-induced twin, you would think more variations, or you get maybe steps in it or something like that. But it's always still interpretation. There is not a clear method to say, yes, 100% this is a grown-in twin, or 100% this is a deformation-induced twin. Yeah, and if you anneal them, they tend to be getting more coherent, because annealing would serve to allow the material to find lower excess energy states, and this means it likes to form the twins, the coherent twins, if there are already twinned structures available. But it depends on the kinetics of the process, like how high is the temperature and how large are activation barriers for the jump, specifically in this already twinned structure. So it depends very much on the material, how long you would need to wait. And then also it depends on stacking fault energy of the material, because in general the twin boundary energy is related to a stacking fault energy. And this can be very different for different materials, right? So there can be almost 2 orders of magnitude, 1.5 order of magnitude variation between the stacking fault energies of different materials. And so that all affects how an annealing treatment would serve to get more coherent twin boundaries. But in all materials, the general direction would be if you anneal, you get more coherent boundaries. Yeah, and still you see that you can still, in real materials, you always have to identify a grain boundary with a certain thickness. So whenever you do thermodynamics and Gibbs thermodynamics, you know that you always work for that you describe interfaces with a mathematical plane, the Gibbs dividing plane, right? So you project the excess quantities of the volume, which we call grain boundary, onto a mathematical plane. And it works because the beauty of the Gibbs approach is that the position where you put this mathematical Gibbs dividing plane is, can be varied without changing the result. So this means that the Gibbsian description of having a mathematical 2D plane as a boundary between phases, for example, can also be applied to the grain boundaries or to phase boundaries. But if we think of a diffusive process, we really have to go from the continuum description based on Gibbs to the local atomistic description, and then we have a grain boundary zone, a slab of a certain thickness. And this is very nicely shown by, now we are going to state-of-the-art computational modeling. So this is showing you the model or result of a modeling which was done by Tim Frolov a couple of years ago. And it shows you a system which seems to be unrelated to high entropy alloys, but I think it has relevance for this course. This is why I'm showing it. So this is a mathematically pure copper crystal, and it's a bicrystal. So basically it's 2 crystals which have given defined misorientation and a given defined grain boundary plane with a given defined inclination. This gives you this copper sigma 5 310 grain boundary. So it means sigma 5 is the CSL description. So 1/5 of the atoms in the grain boundary plane are belonging to both lattices of the 2 grains that come together, and the 310 is the normal of the plane which has been inserted in this misorientation configuration. Computations were done at 1000 Kelvin, so jumps are sufficiently quick to be covered by MD, molecular dynamics simulations. Very importantly, it is connected to an open surface, so excess volume can be exchanged with an infinite source or sink. Doesn't matter. And what you see here is a region where the atoms have different color. This is the grain boundary. And you see they have 2 different colors, red and lightish blue. And if we zoom in, as shown here in the bottom parts, this one, then you see that the local structure at the boundary plane of given misorientation of a given material at a given temperature can be different. So you have this, what has been called the kite structure, the bluish one, of the grain boundary zone. But also there are atoms which are situated in this split kite configuration. And you see there's a small difference, but there is a difference. And the local distribution of excess volume along the boundary plane varies. And I think conceptually you can directly grasp this will affect diffusion, right? And the nice thing is, with this MD simulation, you can also simulate diffusion processes in the boundaries for these 2 different structures of the boundary plane. And this has been done. And you see here that there is basically a crossover between the grain boundary diffusion, so this is dGB, as a function of 1 over T. And for the split kite structures and for the kite structures, you have a crossover. You have at a given temperature different values of the diffusion coefficient. And because you have a crossover, it means you have different slopes. So the activation enthalpies for diffusion in these different structures vary. So activation enthalpy is just a slope in this representation, right? And the nice thing is that this was actually found in experiments 20 years earlier, but actually from my lab, but that was before I was there, not so old. At that time it was just a fact, but not an explanation, because we couldn't, or people couldn't explain why this happens, because it's against the structural units model, right? Because at a given material, given misorientation, it should be a given configuration. So you would expect diffusion to vary consistently with 1 over T. And you would not expect to see something like kink. It's for many materials that have been investigated. And this is a not so fair answer, because the reality is not so many materials have been investigated. So I would say probably it's less than 10, where you can have a comparison between theory simulation on one hand and experiments on the other hand. This is also related to the fact that my laboratory is the only one on this planet left that can do these investigations, which is sad.
Calculate delta H by CPT.
I calculate.
How you calculate delta H activation?
You basically just take the slope in this Arrhenius representation, then you directly get the activation enthalpy.
There is a disconnection between this blue and this kite and split.
Yes.
And that is a default. This connection is also.
If you have a disconnection at the boundary, then this will probably affect even more the diffusivity, because it's a defect inside of a defect. So there is additional excess volume associated with disconnections. Likewise with disclinations. So you have then additional stress fields at these points, and yeah, more open structure. So it means that this will accelerate the diffusion. But here we have to, this is a picture showing that the transformation can go on. These diffusion calculations are done in near equilibrium conditions, where only one of the phases would be present. So you would kind of take your system and take the configuration so that either kite or split kite structural units make up the boundary at a given temperature. Then you let your system diffuse, you measure diffusion coefficient, then you change the configuration, you do the same experiment on the computer again. And in experiment, it also is the same. You would see that when you go from a certain temperature low to a certain temperature high, you have not a common Arrhenius line anymore, but you have different slopes in different temperature regions. But measuring in the zone where the transformation occurs is almost impossible, because that structural transformation would be much quicker as the diffusion experiment would do. Yeah, but then you don't see diffusion. In the computer simulation you could interrupt, but the diffusion is a long time process. The transformation occurs much more quickly. So it's the characteristic time of the transformation is maybe related to local atomic jumps, but when we analyze diffusion, it's long range transport and not the local jumps. You could maybe measure the local jumps in MD, not in experiment, but then you don't get the diffusion coefficient. What you get then is mean square atomic displacement. And that is not really, I mean, you have this Einstein-Smoluchowski formula for relating the two, but in the boundary it's difficult because you also have jumps from the crystal core to the boundary, from the boundary to the crystal core. And so you cannot really make a very immediate connection between mean square displacement and diffusion. And what you would get in general is when you have a transformation occurring, you can always describe it as a front running through the system, right? So here it would basically go from, let's say, the split kite configuration would move along the boundary and would transform the kite transformation that has been present earlier. Any of these transformation fronts tend to accelerate the measured diffusion, because it's not only thermal diffusion then, but it's also this transformation process and locally created excess volume which drives the mobility of the atoms. But it's then a different contribution to mass transport, which we normally wouldn't describe as a pure diffusion process, because there's more than just the response to random motion because of temperature. Yeah, and maybe to show you that concerning structures and not diffusion, this is now can become very difficult, or you could say interesting, because in computer you can always make perfect boundaries. In reality, you need to have a bicrystal, right? You need to grow. If you do this experimentally, you find out that this is not possible really for in a perfect way over long distances. And if you do macroscopic measurements, but even if you do microscopic measurements by TEM, you will see that there are always deviations from perfect misorientation, from perfect grain boundary inclination, and you get also grain boundary curvatures. And in order to analyze this experimentally as well as with computer simulations, we analyzed experimentally a kappa bicrystal. As model grain boundary, we were taking this sigma 5310 grain boundary. And there were deviations, as there always are if you have an experimental system. In the end, we would like to relate this to also grain boundary diffusion changes. So far, we are working on the grain boundary diffusion, but I just wanted to show you how these deviations from ideality, like in your case, non-incoherent twins, are related to structural units in the grain boundary plane. For this, we measure structure with atomic resolution, and we also measure strain fields with almost atomic resolution. And this is the EBSD image, so electron backscatter diffraction. You know also what it is? Okay, it's a scanning electron microscopy based method where you basically look at the signal of electrons which have been emitted by your electron gun, by your cathode, and which have been backscattered from a very thin region of your crystal into a detector which is situated at a certain angle. And so basically because it's a diffraction signal, it's related to the orientation and the specificities of the crystal lattice that gives you the diffraction of these incoming electrons with the outcoming. And so this is a method of looking at the orientation distribution function of a polycrystalline material. Because you know the orientations of the crystals, you also know the nature of the boundaries, the interfaces between them. And this is normally displayed in color codes, and this is shown here. So this is experimental EBSD image of this bicrystal. The white line here signifies the grain boundary between them. And you see that the grain boundary direction changes, which was not intended. But here, this can be regarded as a feature and not failure, because this gives you now the opportunity to, in one material, have different types of high-angle grain boundaries present. And related to your twin sigma 3 question, this is sigma 5, but still a highly symmetric grain boundary plane. And you see that you can in one grain boundary have symmetric parts of the boundary, but you also have asymmetric regions. And by focused ion beam, sputtering with an ion beam in the SEM, so you can select local regions, and so you can cut very small pieces of a material and then look specifically at different regions, so different types of boundaries from the same material.
This analysis was done by which software?
Yes, this was done by EBSD software.
EBSD, TSL or like from MATLAB coding?
No, from provided with this instrument. I forgot the name, HKL or DSL?
HKL is
Yeah.
But because the misorientation, deviation, error in like when you calculate chem, there is first order misorientation. I usually 1 degree. That is like means.
You mean this 38.1?
Yeah, that's very near 39.
Yes.
That is calculating through EBSD. It's like
The recent versions of this EBSD software is actually capable of doing this. You should maybe look into the papers by Stefan Zefferer, because he has developed a lot of this, and this is actually done in his lab. So, because we collaborate on this with him. And so you need really a very modern SEM microscope with all kind of the best electron optics, high resolution field emission, and also you need the new software.
One more question. Why we calculate sigma 5 in copper?
We took sigma 5 because it is a more interesting boundary than sigma 3, because sigma 3 is too low energy, and sigma 5 often is thought of when it especially has small deviations from ideal misorientation or inclination, that it resembles in a good way the random high angle grain boundary, but still has enough symmetry so that you in TEM can maintain the columnar view, because you need to be in zone axis condition in order to get a structural image from high resolution transmission electron microscopy. And if you have a real random high angle grain boundary, then in the grain boundary transition zone you will not have a columnar view, so you will not be able to identify structural units, and you will not be able to analyze strain fields by geometric phase analysis. And this is why sigma 5 is often taken in simulations as well as in experiment as a good model system for a random high angle grain boundary. At copper, because you can grow sigma 5 in copper. This is an art in itself to grow bicrystals, and not for all materials you can do it. And the person who did this is specialized in growing bicrystals in copper, so we got this and we were very happy, because not everybody can do it. I mean, you need to have at least 10 years experience to get a good bicrystal going, right? Because all the small conditions are important to get really a good boundary. And even then, you don't get a perfect boundary. This is the best person can do. Yeah, then we investigate these two regions just for showing you how this change in inclination and going from symmetric to asymmetric boundaries change the structure. So here we directly go to region 2. This is here at the junction between symmetric and asymmetric parts, and this is then high resolution STEM image. So you see atomic columns. We are looking with the electron beam parallel to the atomic columns, and so because this is a CS corrected microscope, so the aberration is corrected, which means that we can identify intensity with position of column. And so it means that we really have here atomic columns where there is a light color, and we do not have atomic columns where there is a dark color. And you can see that for this non-ideal situation, so the ideal misorientation for this boundary would be 36.9 degrees. We have here 38.6. So it's not a high deviation. We are in Brandon criteria limits, so it means we can still describe this as a sigma 5, 310 boundary, but it is not perfectly ideal. Now, what do we have as structural units? You see here, we have these something like kite-like structures, but we also have in between more complex structures which are made out of different structural units. We can call them structural units because they are repeated along the grain boundary plane. So the first and most important condition of structural units model, periodicity along the boundary plane, is maintained. But you see also that the inclination of the structural units with respect to the mathematical grain boundary plane, because this would be something like the mathematical boundary plane, is different, right? So you get this kind of faceting of a boundary. And this is also interesting because when you look at it with more and more high resolution at your grain boundaries in your material, you will see that there is always a tendency for faceting. It could be just very small. So the facet length might be very small so that you only see it if you go to real high resolution methods with atomic resolution. But the tendency is there because then this facet can be filled with one structural unit, and that is saving energy. And so, but then there must be another facet, and this is probably, no, I think it must be a different structural unit or an arrangement of different structural units, as shown here. The beauty is, even though you have this deviation from the ideal lattice, you still can use structural units model because it's a few structural units only, and they are periodically distributed and arranged along the grain boundary plane. And in these cases, we see also that sometimes you get structural units also from a different symmetry, like sigma 5 and sigma 3 type structural units making up the grain boundary structure.
Previously, there is something 8 atomic layer and 7 atomic. What does that mean?
This means if you count now, how many come together, it's different numbers. Is that good or bad?
More the number, more is good.
Yeah, equal number would be good, right? Because then you have more coherency at the boundary plane, less energy. So you have to have additional defects here. How do you call these defects if you have incommensurate region? No, it's a dislocation. You like dislocations in the boundaries. This is actually a dislocation.
I like it, but it's like when we see in TM, dislocation is a number of points are not. If I see only lattice fringes, that's why I got that.
Yeah, here you have a number of atoms because each lattice point here is 100 or 1,000 atoms long, right? Because we just see the projected 2D image of a 3D structure in TEM. That's always the case, always the difficulty.
We are calculating a mathematical function also. Then projection of this.
We can do.
Then we are at
Yeah, I mean, here we don't do any calculation. I mean, we did have Tim Frolov calculate the same structures to compare the experimental results, but I'm just showing you the experimental results. So these are all experimental structures. These defects here, like a new structural unit, can, especially in these cases where you have different number of atomic layers coming together at the boundary plane, be called a secondary grain boundary dislocation. So it's a dislocation because it connects in the typical edge dislocation type, a region where different numbers of lattice planes come together, right? There is a half plane inserted, but this is now a half plane of the grain boundary structure. So the Burgers vector of this secondary grain boundary dislocation will be a Burgers vector which doesn't fit to any of the two lattices above and beyond. But it can be, so this dislocation-based description of grain boundary structures is exactly equivalent to the structural units description. You can either choose to say, oh, there is a new motif, a new structural unit introduced, or you could also say there is a secondary grain boundary dislocation introduced. The meaning is exactly the same. And then if you go to larger inclination deviation, you get to even more strongly disturbed structures. We call this staircase morphology because every second kite-type structural unit is now interrupted by various defects, as you can see here. You can also see that this more strongly, if you now take the dislocation model or description for the grain boundary, you would have a more defected grain boundary structure. But even though you have here less deviation from ideal misorientation, but you have more inclination deviation of the grain boundary plane. So these two aspects need to be considered differently also when you analyze your twin boundary structures, right? So misorientation deviation is one thing, but also how the inclination deviation of the perfect boundary plane normal is there. You have to analyze. And it seems the good news is all these models, dislocation-based or structural unit-based, they still work. So it seems still that you have only a given small number of structural units and the periodicity of them is important and nature maintains that. But when you compare the outcome in terms of higher energy, it seems that the inclination deviation is maybe the more important one over the misorientation deviation. And now we also come to that what you also I think asked earlier, when there is a step, a disconnection at the boundary, what happens? Actually, then you have to worry about long-range stress fields. So what you see here are the results of GPA, which stands for geometric phase analysis. And I think Professor Shankaran will explain to you in one of his upcoming lectures how this works. It's basically a high-resolution transmission electron microscopy-based method because you create a lattice image, right? Like on the left side here. Now, in order to, let me put this as a question. If you see this image, do you think just in, let's say, this red box, is there strain in the lattice or is it looking more like perfect?
Yeah.
Exactly. In reality, we always see a spread of intensity. It's not delta distributed, but it has some distribution in space. So there is intensity diffracted into different k vectors of the Fourier space. And that means strain is in lattice. This is the way how geometric phase analysis analyzes mathematically strain with atomic resolution from high-resolution images. So it calculates the Fourier components of the intensity distribution in Fourier space, then does the retransformation into real space, and you get these spatial color maps or heat maps, which are shown here, which show you for a given component of the in-plane strain tensor of the TEM sample, the distribution in space of these components. So color change means strain state change. And you see you have here at where the step is, you see these lobes of color change, right? And that means that there is a rather far-reaching strain in the lattice because of this disconnection at the boundary. And this is something which will affect diffusion, which will affect stability of the grain boundary, which will affect locally the structure. And it's very interesting that we have here this force or this strain with an inclination to the boundary. Isn't that odd? Because if you would do now this, you can always separate it into two orthogonal components, right? So it means you would have strain acting on the boundary perpendicular and in parallel. And perpendicular is okay, because this is just probably ineffective because there is so much material on the other side that a small strain cannot really change structure. But in parallel means the boundary itself is not in equilibrium. There is a resulting force acting along the boundary plane. This is something which we don't understand, which the modeling doesn't understand so far, but it's something which would be very, very important for the diffusive processes, because you can understand, I guess, if there is strain acting on, but they don't give residual strain along the boundary plane, because you would normally think of mechanical equilibrium. So when you do these calculations, it's always like you calculate mechanical equilibrium. So in total, the material is force-free and local forces counterbalance each other, right? You have this stress field, but then you have the stress field of a dislocation is symmetric, right? So you have compressive and tensile regions. If you integrate in a sufficiently large region surrounding the dislocation core, you will again get stress-free. Here we have not stress-free conditions, so it means that these grain boundary defects, as long as they are there, create situations where we have to treat boundaries and transport along boundaries as acting on under an additional force field, which comes from defects of defects, like these steps in grain boundaries. Maybe the defects are not so high, we don't know yet, because diffusion measurements are still running, we don't have results yet. But it's something which is new and which you will not find in textbooks or papers, because so far this has not been reported. So summarizing structure of high-angle grain boundaries, there are several models. I think the coincidence site lattice model is not really complete in order to describe. Structural units model, even though it has weaknesses, is normally sufficient in order to describe the general properties of, let's say, your ensemble of grain boundaries, but any understanding of specific grain boundary properties and features, I think, need to take into account atomic structure, and I agree very much with what Sutton and Berluffi already in 1987 wrote. We can do this now for simple situations like the perfect copper bicrystal or things like that, but for a high entropy system, this would still be out of what we could do. But I think it gives opportunity also to think of tuning the boundary structure by going beyond what we now today understand as grain boundary engineering. For maybe you who have not yet attended the higher classes, grain boundary engineering was investigated by a Japanese colleague called Watanabe, and he basically described making a better material by choosing a high fraction of these special highly symmetric boundaries, so CSL boundaries with a low sigma value, mostly a lot of sigma 3 and sigma 3 derivatives like sigma 9, sigma 27. But this is just a rather macroscopic approach. What we suggest is that we can basically change the material properties to the better also by changing the local atomic structure inside boundaries. And this is what we think would be a new way to do grain boundary engineering. Now, coming back to diffusion. So we have seen there's a lot of different boundaries. And if we calculate the excess energy of the grain boundaries as function of misorientation, we start with the low angles, then we go like this, and then we have something like this, right? How to make diffusion measurements? Because we have a polycrystal with a grain size of, I don't know, a micrometer or so, but we do it for millimeter-sized specimens. So we have a huge amount of different grain boundaries in there. Isn't that strange? Because we do one measurement and we get one diffusion coefficient for grain boundaries out of it. But there are millions of different grain boundaries. So why is it still valid to do this work? It's still valid because we have this region of low angle grain boundaries. that contributes very little to diffusivity because diffusivities on average are low. We have the special CSL boundaries. Again, there are not so many often, and even if there are many, their diffusivity will be low because diffusivity in the grain boundary scales with excess energy of that grain boundary. And for the rest, experiments as well as simulations have shown that it's rather constant. So it means that for the majority of different high-angle grain boundaries, the specific grain boundary excess energy will be rather independent of misorientation, and that means also that the grain boundary diffusion coefficient will be independent of misorientation. And the other ones where it's very different have very much lower diffusivity, so they don't contribute so much. So this is basically what we measure. Right, so it is valid what we do, and you don't need to worry about it. So we are now going to grain boundary diffusion, right? We have cut out the surface, no dislocations. This is then a simplified view. We have an open surface, which has been nicely polished to mirror finish. And we have some grain boundaries in the material. And for the sake of simplicity, they are all arranged in a way that they would perpendicularly cut the surface. They have an average distance d and a thickness delta. Now there are three different regimes, A, B, and C. If I now have to draw a temperature axis where these different regimes are becoming dominant, how do I need to draw it? So which of the type A, B, C is the one which I need to regard at the lowest or at the highest temperature?
C at lowest and D at highest.
Exactly. So it means that if we go to very high temperatures, the diffusivity in the volume will become larger. Also, diffusivity in the grain boundaries become larger, but the material that has diffused along the grain boundaries also out-diffuses into the volume. And this is why what you measure later on will be affected mostly by volume diffusion. At the low temperatures, we can effectively say volume diffusion has been frozen out. So it means it's maybe between 1 and 5 interatomic distances, something which we cannot measure on the macro scale. And then there is this interesting regime B, where we have both. We have some volume diffusion. We cannot neglect it, especially because there will also be some out diffusion from the grain boundaries into the grain interiors, but we will also have dominant grain boundary diffusion. Under this kinetic regime B, we cannot independently and directly from these diffusion measurements measure the grain boundary diffusion coefficient. What we will measure is the so-called triple product, P. Well, this is the triple product. And it's having three components, as the number says. S is the so-called segregation factor. Delta is again the grain boundary width. And dGB is the grain boundary diffusion coefficient. So it means we have to take into account when we do measurements at specific temperatures, we have to know in which regime we are. And we, for certain materials, need to know, is there segregation occurring in a measurable, in a strong way at the grain boundaries, or is there not any segregation or very, very close to unity? It also means that by doing these measurements in a clever way, we can get a very good quantitative measure of grain boundary segregation occurring in a material, much better than by atom probe, not because it's more sensitive, but because you get a macroscopically averaged value over all the grain boundaries. Because when you look with atom probe tomography, this is a method you know, you have a very small tip which has a radius of curvature of 10-20 nanometers, which you prepare of your material. And you apply it now at low temperatures into a very strong electrical field with electrical field gradient. So basically you field evaporate atoms from your tip. And the probability for doing this field evaporation is basically much higher for the highest terraces of atoms than for the lower ones, which means you kind of evaporate first one layer, then the next layer, then the next layer. And so since these atoms go through a multi-channel plate, so different holes, and then go to a mass spectrometer, you get chemical identification of the atoms by mass spectrometer, time of flight mass spectrometry. And from knowing that they come from a certain given terrace and going through multi-channel plate, you can reconstruct in 3D where the atoms you register came from. So you get a 3D reconstruction atom by atom, but only of 50% of the atoms. And that gives you very accurate description of grain boundary segregation, for example, right? Because you know, in this grain boundary, there were 3 out of 10 atoms, another element or so. But when we do this for different grain boundaries, in different high-angle grain boundaries in the same material, we see that this segregation can vary quite drastically. And we so far don't understand exact reasons for it. I suspect what I showed you for the pure copper, that small deviations in inclination, in misorientation of these boundaries serve to have different structural units with different distribution of excess volume, which means the local chemical potential for desegregating species to go or not to go to these places will be different. And this is what we see in the end without having the detailed knowledge of the reasons, but it's, I think, a good concept to work with. And so from these diffusion measurements, when you measure diffusivity and you know the grain boundary width, you can twist the whole thing round and take this as a segregation factor measurement, but then for your entity of all the grain boundaries that are in your volume. So you will get only an average value, but very often that average value is what you need and not the specific local values you measure. It will be calculated by this equation, because you then
As segregation factor.
as segregation factor, yeah.
By which method calculate?
First of all, you get the segregation factor out of the measurement directly if you know DGB, if you know delta, and if you measure P. Right, and then you use Gibbs adsorption theorem in order to calculate, to transform the segregation factor into a concentration at the grain boundary. If we are again in this complex type D diffusion regime, the good thing is that we don't need to worry about the amount of tracers we applied, because this is also something which you have to worry about in the experiments, because if you apply less tracer, it will be completely consumed during the diffusion experiments. So you have instantaneous or thin film source solution of your diffusion equation. If you apply a little bit more, it might not be consumed, so it's like a constant source. But if we just look at the solution for B-type diffusion regime, we see that although there is a difference in the magnitude of the calculation, the trend with Z, which is the important quantity for calculating the diffusion coefficient out of it from the slope, will be the same. So there is no difficulty. Last things for today, transparency for today. This is now a real measurement. So we have now here a measurement, grain boundary diffusion as a function of 1 over t multiplied by 10 to the 4. And I now have here two sets of data which are kind of connected by this rather sudden jump, right? All of this are experimental data, and it's described in this funny way. And there's also different descriptions here. What do I see here? I do see here a measurement series where the temperature has been changed from low to higher temperatures. So effectively, I'm going from type C kinetics, only grain boundary diffusion measurable, to type B kinetics. Grain boundary plus volume diffusion is measured. So it means I have to calculate or to remember that the mathematics of the diffusion description changes. So I have a dependency of segregation factor here also, and I have a dependency not depending on segregation here. So it means this is exactly the way you can either determine the segregation factor, or if you, for example, have made sure that your segregation factor is unity in all cases, so there is no segregation occurring in your material, then this is a nice way of measuring the grain boundary width, because then I can just plot DGB. I plot the triple product where S equals 1, and the difference then just gives me the delta, which is the grain boundary width. This has been done for many, many pure metals, for alloys, for high entropy alloys, and from these measurements, nanometer has been established. So this is why we know that the grain boundary width, this transition zone in a high angle grain boundary, is 0.5 nanometer for basically all metallic materials that have been tested so far. So clever combination of C and B type kinetics can give you this type of description. Okay, great. Then thank you for being here.